All right, let's do an Atwood machine with static friction. So the idea here is that we can just keep piling on mass over here, piling it on, while the system is totally static. And then eventually we're going to get to the point where this mass is large enough to cause this to break loose. So throughout the entire analysis, we don't have to worry about acceleration. We're just trying to get the information in there that the static friction force is maxed out. It's right at the point where it's about to let go. So I'm going to have to do my standard analysis where I break the force of gravity into tilted components, and I look at the normal force pointing up along one of those tilted axes. Let's get the force of gravity in, that's straight down. So that's going to be, I guess I'll work over here. It's going to be mg. May as well put a number on it right now. I have a 5 kilogram mass, so this multiplies out to 49 newtons. I then look at the components of the force of gravity. Again, we're building a right triangle here by projecting the force of gravity onto this axis. And as usual, it turns out this angle is the same as the angle of the incline, so it's 30 degrees. And that's going to be the adjacent side, so I'm going to have mg cosine theta for that component. So that gives me 49 cosine of 30 degrees. Go ahead and put a number on that real quick. And I get 42.4 for that. Then I'll look at the parallel component. So that's equal in length to this little chunk. But I'd rather look at it attached to the mass. So that's going to be an mg sine theta. That's 49 sine of 30. And 30 degrees is a special angle. The sine of that is 1/2. So I end up with a 24.5 out of this. Okay, I have friction forces involved, which means I care a lot about the normal force. And I've got nothing else going on in the perpendicular direction. So that normal force must exactly cancel the perpendicular force of gravity down here. So that's going to be 42.4 newtons. All right, and finally, I've got to figure out which way the static friction force points. And the idea is that I'm breaking loose and taking off up the ramp, which means the static friction force must have been holding me back down the ramp before it broke loose. So I'm going to put it there. Furthermore, we're looking at a breakaway phenomenon, which means the static friction force is at its maximum possible value right now, and it's just about to give up. So that's when we're able to use this formula, that it's equal to mu s times the normal force. And mu s is 0.7. The normal force is 42.4 newtons. And I get 29.7 newtons for the maxed out static friction force. I can even put a little subscript of max on there, but I'm running out of space. I have to write really tiny. Okay, and if this thing is just about to break loose, then what we're saying is that the tension pulling in this string, pulling up the ramp, I'm still in equilibrium. That tension is going to be equal to the sum of those two downward forces. So I'm still in equilibrium, but my static friction force is maxed out. So I suppose I could just get a number on it right now. I haven't even looked at the hanging mass there. We'll get there at the very end. So I'm still in equilibrium. So T is going to be equal to that maximum static friction force plus an mg sine theta. And if I even increase T by just a billionth of a newton, it would cause the breaking loose to occur. So this is that cut point that we're looking for. Throwing in the maximum static friction force, that's 29.7 newtons. The parallel component of gravity, that was 24.5 newtons. And I find a tension in the string. That's 54.2 newtons. And that thing is going to be useful, so I'll put it in a box. And then finally I can get over to this little mass and figure out, well, if the tension is 54.2 newtons right at the breakaway, then what mass does it take to create that tension? So I have in the force diagram for this little mass, tension's pulling up, mg is pulling down. And again, it's a static system, so tension's going to be equal to mg. That's not true if this mass is accelerating, where you have to have unbalanced forces. Well, in this case, they're still balanced. It's still a static system. So I'm going to write down T is equal to mg. And I had 54.2 newtons of tension in the string. I'm trying to find out what mass would create that tension. And I can solve for m quickly here. 54.2 divided by 9.8. And I get 5.53 kilograms. Again, I usually work informally with significant digits so that I don't have to worry too much about like stating a static friction coefficient to 3 significant digits.